All right, good afternoon, everyone. Today it's my pleasure to introduce Hansol Ryu. Hansol received her bachelor degree from the Korea Advanced Institute of Science and Technology in 2014, with a double major in mechanical engineering and computer science. She then spent the next 2 years studying her master's degree in the same institute, during which she investigated anterior-posterior ground reaction force using a compliant-legged walking model. Her master's thesis was a success as she patented this compliant leg model afterwards. Hansol was also a member of Engineers Without Borders in her institute and was involved in a project developing affordable weather observation systems for remote villages in Nepal. She also volunteered to translate over 20 TED Talks from English version into a Korean version. Currently, Hansol is a visiting graduate student in the HBL under supervision of Dr. Art Kuo. Her research project at the University of Calgary focuses on the interface of neuroscience and biomechanics. Using the knowledge she learns, her personal goal is to build a prosthetic hand that is able to play the piano. So Hansol didn't mention this, but I assume that this prosthetic hand, her goal would be to have it highlighted on the HBO TV series Westworld. And if you don't know Westworld, just search the introduction after the seminar. So in her free time, Hansol plays a Korean traditional string instrument called the geomungo, which is as tall as she is if you stand it up vertically. You're taller? Just taller? Okay. So since arriving at Calgary, Hansol has tried a couple of new sports like swimming, snowboarding, fencing, and scuba diving. Some other fun facts about Hansol is that her favorite food, above all others, is grapefruit, and also that she will not eat a single food without some form of utensils. So no matter what it is, whether it's fried chicken or maybe even the grapefruit, she would have to use those utensils. So today, Hansol will tell us a bit more about her research, which uses optimal control theory in engineering to answer a question in neuroscience. So do animals need an internal clock to generate cyclical movements?
Thank you for the introduction. Please welcome my guest. Have you ever felt like we have an internal clock that will generate cyclic movements like walking and running? Maybe like this. Maybe we have an internal clock that will send us some command so that we can walk at certain frequency. But what is that? It's not likely that we have some physical clock inside us somewhere, so it should be something biological. There have been researches about central pattern generator, or CPG, that can generate cyclic movements without feedback. So this is a model of CPG and looks somewhat complicated, but how you understand this is by seeing there are two sets of neurons that will alternate each other. So it is reported that lampreys use that kind of CPG to generate their walking motion like this. And what's surprising is that you don't even need your own body to generate rhythmic movement, meaning that you can disconnect the spinal cord from the body, so nothing can really move around. So therefore, there's no sensory feedback going in. It can still generate pattern like this. So that is called fictive locomotion, when isolated spinal cord generate patterns without movement or sensors. You're seeing somewhat altered pattern compared to intact movement, but still it is generating some pattern without any sensors. So this is just another version of CPG. there are two sets of neurons, and we call each set as half center, and they are producing motor commands. And it is a conventional way of representing CPG that you connect two sets of neurons by these mutually inhibiting connections. What I mean by mutual inhibition is that if one thing is firing, it will inhibit another, so they will stay quiet. And then when it fires, the other one will be inhibited, so it will alter to generate pattern. Well, we can adapt this structure to our working model. This oscillator can drive walking without any feedback. Well, sounds cool, but the problem is life is full of unexpected surprises, like maybe you can hit a rock during your walking. Maybe there can be a gust of wind. And what's wrong with having just CPG alone? So let's look at in more detail. So for example, it has unexpected ground contact like this, but your CPG doesn't really care what happened, and you will keep generate the rhythmic movement. So blue leg will try to keep swinging forward, and then red leg would keep trying to move forward. Then what happens? Words. And your CPG would just keep generating pattern. Sounds like something's wrong. And then, is there another way? Yeah, sure. Maybe you can rely on your sensors and throw away that stupid CPG. So the idea is you sense something and convert that into motor command, just like sensor reflex. It is also known that sensor reflex can also generate cyclic movements. An example for that would be infant reflex, just like infants grabbing something on their hand. It is a reflex that when you lean an infant forward, or when an infant touches some edge, they tend to step, even if they've never learned how to walk. So it sounds like we can just use sensor reflex for walking. Maybe like this. So you sense something, and that is converted to motor command like that, and it is enough to drive the walking. However, life is not that easy. We all have imperfections, and sensors are never perfect, and sometimes it can tell you some incorrect information. So for example, here, the red leg didn't touch the ground yet, but the sensor thought it touched the ground by some noise or something. So it is telling incorrect sense of ground contact. And then what happens? Red leg now thinks that it is contacting the ground and it is now a stance leg. So it tries to push the ground, while blue leg thinks it is a swing leg now and tries to swing forward. And what would be the result again? Yeah, it fails again. So for summing up a little bit, there are two conflicting ideas of generating cyclic movements. On the one side, there is central pattern generator, CPG, that generates rhythmic motor command without any sensory information. And on the other side, there's sensor reflex to generate motor command, now without a pattern generator. So what's going on? What is generating pattern? Actually, both are working together. It is reported that it is better to have both. But the problem is that we don't know how to integrate two. These competing ideas, this conflict between two ideas goes back to 100 years ago. Like here, Graham Brown suggested that CPG like this, even if he didn't really call it as CPG, but he just called it as two half centers mutually inhibiting each other, can generate cyclic movements like stepping. And about the same time, Sherrington suggested that sensor reflex can generate rhythmic motions like stepping. And it is not only the old problem, the conflict still goes on. There are groups of engineers who build their robots based on CPG here. So it looks a bit more complicated, but the idea is there are two sets of neurons alternating each other. So this one is Salamandra robot based on CPG from EPFL that can swim and walk and change the gait. On the other side, there are robots based on sensory data. So this is Atlas. It can walk on a rough terrain, it can open the door, it can even backflip. So it seems like there are two nice ways to control the robot. But the problem is that we cannot combine two, and two groups are not super happy with each other. So I'd like to suggest a way to make them happy with each other by combining two ideas. So I will suggest an optimal integration of CPG and sensor reflex, and I will do that by using control theory because I'm an engineer. And then I will demonstrate the optimal integration with working model. And then I will use adaptive neural network to implement the suggested network. So for the first part, I will first introduce the concept of state-based control, and then we'll tell about what is the source of that state. There will be two sources. One thing is internal model, another thing will be sensors. And then tell you how that can be viewed as CPG. So about state-based control, it sounds somewhat technical, but what I mean is control is really based on state, not based on time. Maybe you can control by recording your motor command in advance and just play that in the time, but now we are not doing that anymore usually. So like in Atlas, there is a controller, and controller is using states. Here Q means angle and Q dot means angular velocity. So it is not really a pre-programmed command, but it is using the state as its input. But what is the input state here? What do we mean by we are using the state? Actually, there are two sources of states. One thing is internal model, another thing is sensors, but they are both imperfect. So talking about the internal model first, let's say you have a current state like this and know how much torque is applied. Then if you know about the characteristics of your system, you can predict what will be the next state. So like this. But on the other hand, you also have sensors. You can just measure the angle. But the problem is that they may not agree. Sensor can be wrong. Maybe it's telling you wrong information. But maybe your prediction can be wrong. Maybe there was something unexpected happened, like strong wind blown or something. Then what should we do? You can decide on how much you trust on your sensors. If you don't trust your sensor at all, so zero trust in sensors, you can just throw that away and then use your predicted state as your next state and use that as your control input. But maybe you think your sensors are quite good and give infinite trust in sensors, then you are throwing away about what you thought about what would be the next state. And then in this case, measured state would be your next state and will be used to control the system. But you don't need to choose between two. You can do something in between. So I said it is zero trust in sensors. So let's define some number that is showing how much you trust the sensor. So starting from zero trust, L equals 0. And you can go to infinity, but you can stay somewhere in between, like this. So this is how state estimators work. They integrate predicted and measured states like this, and they can adjust the L gain based on how much they trust sensors. And what we can predict from this one is that maybe both ends would be bad. It is bad to rely totally on predicted state or totally on sensors. But maybe best thing to do would be somewhere in between. I will go back to that point later. So I introduced about the state estimator, but how is it related to CPG? So I mentioned that it is a conventional way of representing CPG. There are two half centers that mutually inhibiting each other, and motor command comes out of the input, out of the half centers. But what we suggest here is that we can design CPGs like this. Actually, you don't need to worry about too much of detail of the connections. But what I did here is I designed CPGs to have neurons that represent the state of the system, like leg angle here, and angular velocity, ground contact, and then define the connections so that these neurons can predict the next step for you. So it is just a graphical representation of the equation of the motion. And what is the benefit of doing this? Now you can see first layer as internal model that captures the characteristics of the system, and another layer as state-based control. Then you can map that into control systems representation. There is a standard way to represent control systems for engineers. So here you have internal model and state-based control. Then we can benefit from our knowledge of control systems. And one of the knowledge is that we know how to use the sensory information optimally. So we can add that to our CPG model. And maybe you can notice that there's L, how much we trust on our sensors. And we can do the same thing here. So here I introduced the concept of state-based control and told you that there are two sources of that control. It can be internal model and sensors. And state estimator can decide on how much you believe in sensors. And also I suggested that the state estimator can be viewed as a CPG. And we know the optimal integration of sensor feedback to this circuit. And also our prediction is that maybe two extremes are both bad. Feed forward or using only CPG alone would be bad. And feedback alone or using sensor measurement alone would be also bad. And the optimal would be somewhere in between. So let me demonstrate it with our working model. I will control the working model based on states, as I introduced earlier. And then I will show you how bad it is to use pure feed forward or feedback. And then I will show that best performance can be obtained by optimally using both. So I mean having optimal state estimator. And then I will tell you that fictive locomotion, that the surprising feature of CPG, can be also generated from our model. So here is how we defined our working model. We modeled legs as like this. There's mass and then legs and arc foot. And we have CPG, as we designed earlier. And it is sending motor command to legs. And we are measuring leg angles and also measuring ground contact. So the reason I modeled the human walking like this is based on previous studies. So the model was simple enough, but it captures necessary characteristics of human walking. And also it is feasible to make into robot so that it can really walk. So I defined my model to be controlled dependent on state. So these hip torques are the function of leg angles and ground contacts. And this is how it looks like when I simulate it with MATLAB. So again, the torque was dependent on leg angles and ground contact. Oops. So let's see how pure feed forward and feedback is bad. So to graphically show that, I'm introducing state space representation. It is representing leg angle and angular velocity at the same time. So stance leg movement would represented like that, and swing leg would look like this. And if the model is steadily working, it will just keep repeating on the same cycle. But if something bad happens, it may just go away. So pure feed-forward is bad. How bad is it? And what I mean by pure feed-forward is that we just have internal model and copy the torque from the internal model, but we don't give any feedback to the internal model. And the problem is that there always are noise and disturbance and some unexpected things. And when I simulate this, it's really sensitive to noise and it's easy to fall like this. Yeah, then now let's try feedback. We can collect the estimation error by telling the measurement to internal model. But the problem is that sensor feedback is also noisy. So if we just rely on feedback, it will be also poor like this. So if we think about the gain again, how much you trust the sensor. On the one extreme is you can just rely on command from internal model, just throw away sensor feedback. That's feed-forward way, and it's sensitive to process noise. On the other end, you can rely on sensor feedback. Then it's too sensitive to sensory noise. But there can be an optimal combination in between. If we balance between process and sensory noise by selecting a proper sensory gain. And how do we select sensory gain? Now I'm going back to engineering approach, and there are known solutions about how to optimally select the gain for this kind of situation. Simplest way is just to use method command like this. So by balancing between process and sensory noise, I got a better result. It's more stable to disturbances and has less variability like this. So I can tell the performance with numbers like this. We are testing various sensory gains, and I normalized it with optimal gain. So predicted optimum would be denoted as gain 1, and less than that, so going toward 2, feed-forward, and gains bigger than that will be going toward 2, feedback gain, feedback. So first measure would be energy, how much energy is spent to go a certain distance. That is cost of transport. And as I predicted, it is the best to use the predicted optimum gain, and cost increases as you vary the gain outside of that optimum gain. And one thing to notice is that pure feed-forward was really bad, that I needed to break the axis like this. And also we can measure step length variability. Then we got minimum step length variability with predicted optimum. Also, we can count how many faults were there. So I am measuring mean time between failures. The longer you can go before you fail, the stable you are. So with predicted optimum, it was it could go the longest way or longer time than other gains. So here I demonstrated that it is really essential to balance between process noise and sensory noise by selecting the feedback gain well. So another thing to demonstrate with our model is whether it is capable to generate fictive locomotion, whether it can work without any sensory feedback. Yes, it works. I can cut connections between my controller and the body, and it's still producing fictive locomotion like this. There can be multiple ways of calling the signal. Maybe you can cut here or somewhere else, but they can both generate fictive locomotion like this. So I introduced my model that is controlled based on state and demonstrated that pure feed forward and pure feedback are both bad, and best performance is somewhere in between when you optimally balance both gains. And I also demonstrated that fictive locomotion can be generated from our model. Okay, great. But it's not biological. I was an engineer who designed all the different circuit, but can biological system do that? Maybe. So that is the motivation for the last part, adaptive neural network. So I will suggest that a simple neural network can learn to be a state estimator, and it can also adapt to a new condition. So if a simple neural network can be a state estimator, maybe we can have something similar in our nerve system that can do state estimation. You don't really need to worry about all the details, but if I tell you briefly, it is using its measurement as the input of the neural network. Tapped delay line just means that you are referring to your past history. And then I will multiply some weights to those history and sum them up to generate state estimation. Similar way, I can use inputs. And then I will train the network to adjust these weights to be a better estimator. And it is an adaptive filter that can learn real time. So it learned to be an estimator like this. And then if I change it, the noise condition like this, it adapted to the new condition to get a better estimation. So the idea is the same. When your sensor became less trustworthy, you are reducing weight on sensors, and then increase another weight to compensate that. So it seems like a simple neural network can learn to be a state estimator, and it can also adapt to new conditions to handle external noise and sensory noise like this. So I suggested optimal integration of CPG and sensor reflex using control theory, and demonstrated the best performance with optimal predictive gain with working model. And also to answer that whether a biological system can do that without knowing the control theory, I showed that adaptive neural network can can be a state estimator, and it can adapt to a new condition. So going back to our first question, do animals need an internal clock to generate cyclic movements? Sort of, but we don't need to call that as internal clock. Maybe it's better to call it as internal model. But we also need feedback. And we can integrate both to be a, so that CPG can be an optimal estimator. And also it's learnable from neural network. Thank you.
Any questions for Hansol? All right, I can start with the.
Yeah, I was just, how do you think your model works when you change the length of the legs and when you speed things up? So let's say you're a giraffe, and a giraffe is running quickly.
So are you asking that whether my
what happens
model?
to the phase delays? You increase the phase delay of the sensory input coming into your controller. How does that impact your model?
Oh, so you're asking that how the delay in nerve system can affect the model?
Yeah. So let's say the information is coming in at the incorrect point in the step cycle.
The answer for that is that I think the neural network can learn with the delay from the beginning, and then it can train itself to use the delayed information to generate optimal estimation. Does that answer your question? Yep.
Okay, I have a question. In the second part, you said feed forward or only feed forward is bad,
Yep.
and you also only feedback is bad. But I would think in a scenario where there was no noise, that those scenarios would be okay. So how did you pick the level of noise that you input to those sensors in your model? Was that based on biology, or what dictated that noise level?
So that's true that when you don't have any external noise or sensory noise, it doesn't really matter. You can just do whatever you want. But I think for biological systems, it's never perfect. So that is the reason we wanted the optimal estimator. But how we picked the noise level for our simulation was just random numbers that will work.
So was it a magnitude of the signal that was sent, like a percentage, or what did you end up choosing that was for that noise?
So it was something like when the actually I simulated multiple cases of the noise level, but the extreme case was something like 10% of the movement range.
Was the extreme the upper end of it, or?
Yeah, it was. I mean, so when I used 10% of the moving range, let's say leg angle was between 0 to 30 degrees, and I added 3 degrees of noise all the time. And then that was really an extreme case that the models using L gains other than optimum would really fall over again.
Okay. Yeah.
So yeah. Scott?
Was the noise always symmetric?
Was the noise
like
symmetric?
normally distributed?
Yeah, it was normally distributed, zero mean, and defined by standard deviation. I chose that noise because the solution for those noise is known for engineering systems. But for adaptive neural network, it doesn't need to be noise like that. But I haven't tested
Do you plan
yet.
to explore it something like you mentioned wings,
Yep.
right? So that wouldn't be normally distributed. It would be like unidirectional, right? So
Yeah,
it
they
always
will-
pushing one way or
Uh-huh.
the other.
That will have noise mean non-zero value.
Yeah.
Yeah.
You plan to explore that too.
Mm-hmm.
So it's easier to conceptualize these two options as feed forward and feedback.
Uh-huh.
Is there any possibility there's something different, like a single system that has the properties of both?
Single system has properties of both. Can you explain more in detail?
So this has bothered me for some time, in that people seem to be able to adapt to circumstances and optimize their energetic cost very quickly.
Uh-huh.
And I was talking to a fellow at Georgia Tech who said something very interesting to me. The brain knows how hard it's working.
Mm-hmm.
And so if the brain's sending out signals according to the feed-forward system, but then it's assessing how much it's getting out of that, that doesn't have a feedback component to it, other than it's all tied together. Is there a possibility that the system works in something that is not feed-forward or feedback, or a combination of the two, but it's something in between that works the same way as the two?
That's not either feed forward or feedback, but something in between, but can work as two. I guess
It has the same outcome.
that has the same outcome. I guess maybe that is the case where condition doesn't really change. So like you are born with some sensors and the noise from the sensors would be always constant, so that you don't need to adapt all the time, and you just use fixed gain all the time without considering feed forward or feedback. I guess maybe we can talk about that later.
Yeah, another question then.
Okay.
In the third part, you showed the new condition. And when the system was learning this new condition, like what would that be equivalent to? Is that as if like the dynamics of the system have changed, or what is, you look like you changed the noise in there, but you know, in terms of say a human, what would that be equivalent to, like that new condition that you were modeling?
Then new condition I'm modeling. Then new condition can be some environmental change if I'm changing process noise, not sensory noise. Then something like a sudden wind blows or something. I don't have a really clear example of sudden change of your sensory noise, but it can be something like you are entering into more confusing environment, something is distracting you, and as you said, maybe change of body parameter can be another scenario, which is not handled in this presentation yet.
Okay.
Do you think the optimum gain is different across different animals? Like, I was thinking, if you have 4 legs, do you need less feedback, or like versus 2 legs?
Oh, that's a good question. So I think, yeah, optimal gain depends on your body parameters and your sensors and what environment you are dealing with. But that invites another question about whether all the animals need that fancy tuning of your gain. So for example, if you are 6-legged, maybe you need to worry about falling less than humans do. Then maybe it's okay to just choose gain not that exactly. Or possibly it's okay to use feed forward more.
Graham?
Do you guys be fatigued that you'd use one more than the other, feedback versus feed forward? Or does that change based
So-
on
So when you are fatigued?
Yeah. I'm just thinking about
Mhm.
going out for a run or something like that, and just start running, and I sort
Uh-huh.
of stop thinking about what I'm doing,
Uh-huh.
and sometimes I can trip or something like that, or is there something that you start to shift towards one that you burn?
That's an interesting point, and I've never thought about that before. But I think the answer is how you define the fatigue. So it can be something like when you're fatigued, it can be that you are less sensitive. So maybe you can have more sensory noise than before. But it's also possible that when you are fatigued, your muscle is less accurate for your command. So send some command, but muscle is not able to really generate that amount of force. So then it is more process noise, the other side. So I'm not sure whether which one dominates another, but that can be an interesting question.
Francie?
When you say sensory input or feedback, does that assume like we mean all the senses that we have theoretically, like, or is it just proprioception and like touch, or would that include vision and hearing?
Oh, okay. So the question was, when I talk about the sensory measurements, do I include all the possible sensors we have in biological system? Is that? So here for simulation purpose, we used minimum amount of measurements, which are just leg angle, that we can get from somatosensory input or maybe from muscle spindle. But we don't have any point about what that really is in biological system. Yeah, there also can be an interesting thing to research about when you have multiple sensors and they are measuring different things. Like one sensor was measuring your error, one sensor was measuring your absolute value, how to use both to get an optimal result. So that can be another interesting thing to do next.
Looking at your neural network model, in terms of, it looked like quite a simple architecture. In terms of speeding up or have you looked at how to speed up your learning rate or the time that it takes for your neural network to learn by looking at different architectures, or do you think there's improved architectures out there for it?
Sorry, can you ask the question again?
Well, in a biological sense, if your neural network model is, say, learning from a fairly stable state, and then you put it into a more perturbed state, we've talked about the level of noise increasing, with sort of a step change there. Have you looked or thought about ways that maybe your neural network architecture could adapt to that state faster? That learning rate could improve.
So are you asking about the situation where a biological system enters into default condition, or?
So just more, how fast does your network learn? How many steps will it take for it to adjust to a step change in noise?
How fast my network was able to adapt to the change? Actually, it takes quite a lot of steps. Maybe I can go back. Like here, 10 to the 4th steps. So order of 10,000 steps.
So do you think that there's more effective architectures out there, or improved architectures that can reduce that time for learning?
I think we can reduce the time by adopting some different features of adaptive neural network. But here, the weight updating rule was the simplest one, that you just calculate the gradient to adopt, and then have some value multiplied to that and change the weights with that amount. But you can always change the learning rate based on the condition change, like right after the condition change, maybe you can increase the learning rate so that you can quickly adapt to the system, and then reduce the learning rate later to make it more stable. So I think using that kind of technique, I can reduce the learning time.
Just going more on the learning rates, have you done a sweep of different learning rates and looking at which one can adapt the fastest or has the least amount of errors?
Have I tried different learning rate for this?
Yeah, like
Is that your question?
do a whole bunch of runs with a full range of learning rates
Mhm.
to optimize those parameters for the neural network, as well as maybe changing the number of hidden layers and stuff like that.
Well, I'm still working on this, so I've not tried a whole bunch of the range, but I tried several learning rates. And the problem with high learning rate was that the weight tends to oscillate with higher learning rate. And yeah, with smaller learning rate, the problem is just that it takes so much of time to adapt. So I'm showing the learning rate somewhat in between, but it needs more analysis about what would be the optimal learning rate and whether I can just pick a single learning rate that can adapt in a reasonably short time without oscillating too much.
And are your inputs and outputs, are they continuous, or do you discretize them through like a tile coding or some method of reducing that spectrum?
So for the adaptive neural network, I discretized the time, so it was constant sampling frequency.
And your sensor values as well?
Yep.
Or were they continuous variables?
They were both discretized with the same sampling rate.
So what's the purpose of the having a good working model like so where is the possibility to use this kind of a good model in the real life?
So for me, the purpose of this research has two aspects. One thing is understanding what biological systems are doing to generate rhythmic movement. And another thing would be more application side, like building a robot. And so for example, the salamander robot I showed you is using central pattern generator, but they also reported that, it is good to have sensor feedback somehow, but we don't really know what is the way to integrate sensor feedback. So by showing that we can view central pattern generator as state estimator that we know and that we can design, rather than just having two random neurons firing. We can do more analysis from that point, and then when we want to add the feedback to it, we can do it in an optimal way. So I think it can be used to build a robot with better performance.
Another question then.
Okay.
For that neural network, you had the single layer. Was that meant just to show like a simple gain of like an excitatory and inhibitory circuit within the spinal cord, or what was the goal of just having that single layer?
These were...
Yeah. So was that like the weighting gain you had, was that meant to represent just like simple spinal circuitry, or what was the goal of having that single layer versus like multiple layers?
So are you asking whether is there a reason to only have one layer compared to having several layers?
Yeah. Was it to represent closer to biology of just simple spinal circuitry, or what was the goal of just having that single layer?
It's not really to represent the biological system, because for biological systems, it's possible that they have multiple layers. But here, the reason I just wanted a single layer is I thought that is the simplest possible way to represent the dynamics of the system, because for our model it is highly linear, and I think it is enough to have just one layer. And then I can understand the result like this about how HR changes and how that is tied back to the understanding of changing gain. But I'm not sure whether I can do that with multiple layers. But I think if I want to represent highly nonlinear system, maybe I need to use multiple layers.
Okay. Any more questions for Hansol? All right, let's thank her again for her talk. Okay, and next week we'll welcome Dr. Atsuki Fukutani, a postdoctoral fellow with Dr. Herzog, and he'll give a seminar entitled "Does Residual Force Enhancement Contribute to Stretch Shortening Cycle?" See you next week.